All right, this is Unit 6, Lesson 4, Logarithmic Functions. So our lesson essential question is, how is the relationship between logarithmic and exponential functions revealed in the key features of their graphs? So at the end of this lesson, we'll be able to graph logarithmic functions and find equations of the inverses of exponential and logarithmic functions. Example 1, identify key features of logarithmic functions. So I want to graph y equals log base 2 of x. What are the domain, range, x-intercept, and asymptote? What is the end behavior of the graph? Okay. So y equals log base 2 of x and y equals 2 to the x are inverse functions. So start by looking at the table of values for y equals 2 to the x power, which is the red one right here. Then analyze the table of values for y equals log base 2 of x. Notice that these ordered pairs are the same as those of y equals 2 to the x, but with the corresponding x and y values interchanged. So negative 2, 0.25 becomes 0.25, negative 2, and so on. Next, analyze the graphs of the ordered pairs. So if I look at the red graph versus the blue graph, the logarithmic function accepts only positive input values. So my domain is x, where x is greater than 0. My range is all real numbers. The x-intercept is at 1. So right here you can see the x-intercept. The graph of the logarithmic function approaches x equals 0 but does not touch it. So there's an asymptote at the y-axis. And its end behavior, as x approaches 0, y approaches negative infinity. And as x approaches infinity, y approaches infinity. Okay? So as x approaches 0, y approaches negative infinity, and as x approaches infinity, y also approaches negative infinity. So let's try it. Graph the function and identify the domain and range. List any intercepts or asymptotes. Describe the end behavior. So y equals ln of x. Drag the points on the graph to change its shape. Drag the gray point to change the location of the asymptote. So again, I want to substitute in a couple of different values. So at 1, at x equals 0, it'll be about 1. Okay. And then be about there. Okay, so 1, 0, and 2.7181. So my domain, remember your domain is your x values. So x, where x is greater than 0. Okay. My range is all real numbers. So my y values could be anything from negative infinity all the way to positive infinity. My x-intercept is at 1. And for my asymptote is the y-axis. And the end behavior is as x approaches 0, y approaches negative infinity. And as x approaches infinity, as x approaches infinity, y also approaches infinity. For B, graph the function and identify the domain and range. List any intercepts or asymptotes. Describe the end behavior. So I want for y equals log base 1/2 of x. So drag the points on the graph to change its shape. Drag the gray point to change the location of the asymptote. Okay, so this is a log at 1/2. So it's still going to have a point at 1, 0. Okay. And then it's going to go this way. Like this. Okay, so again, you can substitute points in and solve. You can also graph it on Desmos and look at it that way. So for this one, my domain is still x, where x is greater than 0. Range is all real numbers. My x-intercept is at 1. My asymptote is the y-axis. My end behavior as x approaches 0, y approaches negative infinity. Not negative. As x approaches 0, as I get closer and closer to 0, y goes greater towards infinity. And as x approaches negative infinity, y approaches negative infinity. So as I go towards negative infinity for x, so as x goes towards infinity, not negative. As x gets larger and larger, going closer and closer to infinity, y is going to increase as well, but it's going to increase negatively. Right, example 2, graph transformations of logarithmic functions. So just like we did with absolute value functions, with quadratics, with linears, same type of thing happens. You can move a logarithmic function up, down, left, or right. You can also squeeze it or expand it depending on what you add, subtract, multiply, or divide with from it. So graph the function. How do the asymptotes and x-intercept of the given function compare to those of the parent function? So I have log base 2 of x plus 3. In G, the value of h is negative 3. So the logarithmic function is translated 3 units to the left. Okay. So f of x equals log base 2 of x. So that's the original function. So this blue one. And then it's going 3 units to the left. So 1, 2, 3. It ends up right here. So instead of it crossing the x-axis at 1, it's going to cross at negative 2. So the vertical asymptote and the x-intercept each shift 3 units to the left. So the asymptote, instead of being at the y-axis, is now at negative 3. And the intercept at negative 2. All right, so describe how each graph compares to the graph of f of x equals ln x. G of x equals ln x plus 4. Notice it is not in the parentheses. So this means it's a shift up and down. So it's a shift of 4 up. So it's translated 4 units up. For b, h of x equals 5 ln x. This is a vertical stretch of 5. Same exact rules apply. Remember, if it's in that parentheses, it's going to be left, right. If it's outside the parentheses, up or down. And then it's either vertical or it's a vertical stretch or compression, depending on if it's greater than, it's a stretch. If it's less than, it's compression. Example 3, inverses of exponential and logarithmic functions. What is the equation of the inverse of the function? F of x equals 10 to the x plus 1. Write the function in y equals f of x form and then interchange x and y. So y equals 10 x plus 1. I change x and y. I solve for y. So base 10, so I can use log. So log of x equals y plus 1. I subtract 1 from both sides. So y equals log x minus 1. So the equation of the inverse of f of x equals 10 to the x plus 1 is f of x inverse equals log x minus 1. What is the equation of the inverse of the function g of x equals log base 7 x plus 5? So I write the function in y equals g of x form and then interchange x and y. So y equals log base 7 x plus 5. I switch my x and y. So x equals log base 7 y plus 5. So I can change this into exponential form, remember? So this is my base, this is my exponent, this is what it's equal to. So y plus 5 equals 7 to the x power. I subtract 5 from both sides, so I get y equals 7x minus 5. So the equation of the inverse of g of x equals log base 7x plus 5 is g of x inverse equals 7x minus 5. All right, so let's try it out. Find the inverse of each function. I have f of x equals 3 to the x plus 2. Okay. So I have y equals 3 to the x plus 2. Okay, I'm going to switch my x and y. Now I'm going to solve for y. So in this one, I'm going to rewrite it in, it's already in exponential form, so I'm going to write it in log form. So my base is 3, my exponent is y plus 2, and my solution x, so 3, so log base 3 of x equals y plus 2. So I changed it from exponential to logarithmic form. I subtract 2 from both sides. For b, g of x equals log base 7, x minus 2. So again, I want to rewrite this. So I'm using x's and y's. I switch my x and y. Okay. So for this one, I'm actually going to add 2 to both sides. So x plus 2 equals log base 7 of y. And now I can have it, so it's actually, I can rewrite it in exponential form. So my base is 7. My exponent is x plus 2. And then solution is y. So I have y equals 7 to the x plus 2. All right, example 4, interpret the inverse of a formula involving logarithms. So a company uses this function to relate sales revenue R and advertising cost A. R equals 12 log A plus 1 plus 25. R is revenue in thousands of dollars. A is advertising costs in thousands of dollars. What is the equation of the inverse of the formula? Which equation would be easier to use to find the value of A for a particular value of R? So R equals 12 log A plus 1 plus 25. So I subtract 25 from both sides, divide both sides by 12, which gives me R minus 25 over 12 equals log A plus 1. I rewrite this in exponential form. So A plus 1 comes over here on this side equals 10. Okay, so remember common logarithm is base 10. 10 to the R minus 25 over 12 power. I subtract 1 from both sides. So the inverse of the formula is A equals 10 over R minus 25 over 12 minus 1. So it's going to be easier to use the inverse to find A when R is known. Okay. But if A were known, it would be easier to use the original formula. So a company uses this function to relate sales revenue R and advertising costs A. R equals 12 log A plus 1 plus 25, where R is revenue in thousands of dollars and A is the advertising cost. Describe what happens to the amount of monthly revenue as the cost of advertising increases. How might you determine the optimal advertising budget? Explain. So I want to know what happens to R when A goes up. And then how might I determine the optimal advertising budget? So as the amount of advertising increases, the amount of revenue increases logarithmically. So to determine a target amount of revenue, if I were to determine a target amount of revenue, and then I use the model to determine how much to spend on advertising to reach that target. Example 5, compare two logarithmic functions. So logarithmic functions can approximate the altitude of a plane over time. Which plane's altitude shows the greater rate of change over the interval? So t is between 10 and 15. So t is less than or equal to t, which is less than or equal to 15. So plane A, its altitude is approximated by following the function a equals 9,200 ln t plus 10,000, where t is time in minutes after takeoff and a is altitude in feet. Plane B, they gave us 2 points, 10 and 37,497, and at 15 minutes, it was 39,449. So I determined the average rate of change for plane A and then for plane B. So I find A at 15 and A at 10 because those are the two numbers that they gave me for plane B. So at A of 15, I get 34,914, and at 10, I get 31,184. So I subtract those two, divided by 10 minus 15 minus 10, which gives me 3,730 over 5, or about 746 feet per minute. And then I do the same thing with the 2 points that I'm given for plane B, which gives me 390 feet per minute. So between 10 and 15 minutes after takeoff, the average rate of change of the altitude of plane A is greater than the average rate of change of plane B. So let's try it. So for which plane do you think the altitude will change more quickly over the interval from 15 to 20? Explain your reasoning. Altitude is approximated by the following function. So same for plane A, the 2 points for plane B. So we know that plane A increases at 746 feet per minute because that's what we found out the last time, while plane B increases at 400 or 390 feet per minute. Found that on the last. So plane A increased at a greater average rate than plane B. Between 10 and 15 minutes after takeoff, and since both follow a logarithmic model, plane A will continue to increase at a greater average rate. So nothing changed. So it's still, plane A is still going to increase at a greater rate than plane B would. All right, concept summary, logarithmic functions. So in graphs, the functions are inverses, so their graphs are reflections of each other across the line with equation y equals x. So again, substitute in the values of x and y. If you're trying to find the inverse of it, flip those values and solve for y. So equations, y equals log of x, or y equals 10 to the x. So again, log of x is the blue, 10 to the x power is the red. So domain for logarithmics are x, where x is greater than 0. Remember that you cannot put in a negative number for a logarithm. It doesn't work. My range is all real numbers. My x-intercept is at 1, and my asymptote is at the y-axis. And it's basically the opposite for exponential functions. So in exponential functions, all real numbers for the domain. So you notice the range and domain, they flipped. And my range is my y values that are greater than 0. So again, my domain and range flipped from logarithmic to exponential. I have a y-intercept instead of an x-intercept. So my y-intercept is 1. And my asymptote also switched from the y-axis to the x-axis for exponential. Okay. For end behavior, it's very similar. As x approaches 0, y approaches negative infinity. And as x approaches infinity, y approaches infinity. And for exponential functions, as x approaches negative infinity, y approaches infinity. And as x approaches infinity, y approaches infinity. And that is the end of Unit 6, Lesson 4.